Let's do a couple of word problems. I have $1,200 to invest. I would like to have $1,500 in 2 years. What annual percentage rate is required if interest is compounded monthly or continuously? Okay, so I encourage you, take a moment, give this problem a try, and then take a look at my solution. Okay, here's a summary of the problem. We have $1,200, we want $1,500 in 2 years. We need to solve for the interest rate if compounded monthly or continuously. Okay, well, to solve part A, monthly is periodic compounding. That means you need to recall the formula for periodic compound interest. Do you remember what that is? Yep, it should be A equals principal P times 1 plus interest rate over n compounding periods times, or sorry, to the power n times t. That's periodic compound interest. Now, if you look back through the problem, we've got several pieces of information. So one thing is it says, for example, solve for the interest rate. Do you remember which symbol that is? That's R. What does it mean that we have $1,200 to invest? That's P. What about we want $1,500 in 2 years? What does the $1,500 mean? That's A. That's the amount of the account or the balance. Now in 2 years, what does that mean? That means T is equal to 2. We're going to let 2 years go by. We're also told in part A to consider interest compounded monthly. So what does that mean? That means N should be 12 months per year. If I go back to this compound interest formula and start filling in, I need to fill in A with 1,500, then P is 1,200 times 1 plus R we don't know, we'll have to solve for it. N is 12, and then N is 12 again, and times 2. Okay, let me just copy this with a little bit of cleanup. 12 times 2 is 24. Okay, a couple of things to notice about this. One is that there's only one place where there's an unknown. So we should be able to solve this by peeling the onion. We'll peel off one operation at a time. Well, what is the outermost operation? The first thing we need to undo? Yeah, it's this multiplication. So I'm going to undo multiplication by 1,200 with division by 1,200, and I have to do it to both sides. This is the step that students generally struggle with. The next operation is power 24. How would you undo power 24? Well, if you're thinking logarithm, there is a way to do it that way, but it turns out that it's going to be better to apply a power to both sides because this power is constant. So we can use a different power to undo it. What power should I put here? 1/24. This is equivalent to doing a 24th root, if you want to think of it that way. So we are going to apply power 1/24 to both sides. The reason for that, I'll leave the left-hand side as it is, 1500 over 1200 to the power 1/24. The reason for power 1/24 is that, remember, when you have a base to a power, then to another power, you can simplify by multiplying the two powers. So I can multiply the 24 by 1/24, and that simplifies down to just a 1 here in this exponent, and a number to the power 1 is just itself. Now, if you're thinking very carefully, you may think, well, we've just done an even root. Maybe we need plus and minus. To be mathematically complete, we could put plus and minus here, but it turns out that only the plus root is relevant. So only the plus root is relevant here. If you do the minus root, you'll get an extraneous solution. So that would be a number that satisfies one of these equations, but not the very original. Okay, so next thing, well, at this point, this is just a number. It's a specific number. If you wanted to, you could put it into your calculator right now and get it. What we now have is a linear equation in R. So I'm going to kind of fast forward here. I'm going to subtract 1 from both sides. And then multiply by 12. Now, just so we're clear, you have to multiply the entire left-hand side by 12. I've seen students make mistakes where they don't put in these parentheses, and so they multiply only part of the left-hand side by 12. Be careful for that, of that mistake. So what we end up with is 12 times 1500 over 1200 to the power 124 minus 1. All of that multiplied by 12, and that's R. And let's do this on the calculator. Let me put this back in math print mode. That does the nice layout for us. 12 times, and then I need more parentheses because I'm going to do a fraction to a power. So I'll hit this button, get the fraction. I have 1500 divided by 1200. Oops, that's too many zeros. And then I need to the power 1/24th, and I think I'll do it like this rather than putting in another fraction. Then I need a minus 1, and then I have to close up the parentheses. So that thing should give us the answer that we're looking for. You give it a moment there, and you get R equals 0.112. Now, usually interest rates are advertised as percentages. So an APR, an annual percentage rate. So probably the best way to express this is to say that the required APR, annual interest rate, is, and then express this 0.112 as a percent. And what is that? That's 11.2%. Incidentally, that's a rather optimistic interest rate. Most of the time, if you invest something for just 2 years like this, you would put it in some fairly conservative investment, and you're not going to get that high of an interest rate for it. But it's the right order of magnitude for um, just as a demonstration problem. Okay, so now all of that we've done was to solve for the interest rate when there's monthly periodic compounding. Now for part B, we're going to consider the case of continuously compounded interest. Okay, do you remember the formula for continuously compounded interest? Yep, A equals P times e to the RT. Now, a lot of these things we will fill in exactly the same way. The A is 1500, the principal is 1200, E2, the R is what we have to solve for, and then this time T is 2. We don't need an N because this is continuously compounded instead of periodically compounded, so we don't need to specify compounding periods per year. Again, we're going to solve for this R, but if you'll notice, this time R is up in an exponent. Before, there was a constant exponent around something with an R in it. This time the R is up in the exponent. That means we will probably need to take a logarithm at some point. We don't particularly want to start with the logarithm because there's another operation here. That's multiplication by 1200, so we should wait and do the logarithm in a future step. So to start with, let's undo multiplication by 1200 by dividing by 1200. So that leaves us with 1500 over 1200, and multiplication by 1200 cancels with division by 1200, and that leaves us with e to the 2r. Now, the exponential operation is indeed the outermost operation on the right-hand side. So now it is appropriate to apply ln to both sides. So again, ln is a function. We are not multiplying by ln. We are going to say that ln of this number, 1500 over, well, let me do that one in dark blue. ln of 1500 over 1200 is equal to ln of this other number, e to the 2r. Now the point of that is that ln undoes e to a power and leaves just the exponent. So the right-hand side will simplify to just 2r. The left I will leave as ln of 1500 divided by 1200. Okay, at this stage, r is out of the exponent, and there's one last operation to undo. That's this multiplication by 2. So I need to divide by 2. And again, think for a minute, where does the division by 2 go exactly on the left-hand side? Well, how about this? I'm going to write it as 1/2 times, just to be different. Right? Remember, dividing by 2 and multiplying by 1/2 are actually equivalent operations. If it helps, you can think of that 2 as being over 1. So that leaves us with r equals 1/2 ln of 1500 divided by 1200. Now let's go to the calculator and see what this number is. I need, how about, I'll type it in this way, 1 divided by 2 times ln of 1500 divided by 1200. And you can see it's not too different. That's because these different interest calculations are not, well, they're not all that different from each other in terms of their values, even though the structure of the formulas is very different. If you were to work for a longer period of time than just 2 years, then you might get very different numbers for these calculations. But so there you go. R is 0.1115 versus 0.11209. And again, we should, well, all right, switch back. Again, we should convert it to a percent. So the required APR is 11.15%. Okay, so there's the solution to this problem. Okay, one last problem. I deposit $5,000 into an account that earns interest at an APR of 8% compounded continuously. How long will it take for the account value to double? So take a minute and try to solve this problem, and then take a look at my solution. Okay, here's a brief summary of the problem. I'm going to deposit $5,000 into an account. It earns interest at an APR of 8%. It's compounded continuously. How long will it take for the account to double? Well, let's think about this. Again, we're going to be dealing with interest rate calculations. What does the 5,000 mean? That's the principal. The APR is 8%. What does that tell us? That tells us something about R. What value should R have in decimal form? 0.08. Be sure not to make it 0.8. You have to shift the decimal point 2 notches. All right, compounded continuously, that means we're going to be using what formula? PE to the RT. How long until it doubles? Well, how long? That means we're going to solve for, what are we going to solve for? Time t. And then how long to double? Well, the account being double, what does that mean? That means that the account should reach 10,000. Right? It started at 5,000. Double means that it's going to end up at 10,000. Okay, so let's set all of this up. I have A equals 10,000. P is 5,000 times e to the 0.08 t. Okay, now that we've set this up, how do you solve this? I have to start by undoing multiplication by 5,000. So I will divide by 5,000 on both sides. That reduces to just 2 on the left, and on the right, we'll be left with 0.08t. Okay, now the t is up in an exponent. How do we get to it? We'll apply ln. ln is a function. We need to apply it to both sides. I need ln of 2 equals ln of e to the 0.08t. The point of doing that is that ln of e to a number simplifies down to just the number. So the right-hand side, ln of e to the 0.08t, simplifies down to just 0.08t. There's one last step. I need to divide by 0.08 to undo this multiplication. So we end up with ln of 2 divided by 0.08 equals t. Again, going to the calculator, ln of 2 divided by 0.08 gives me 8.66. Now, the interpretation of that is that that's how many years it will take for the account value to double, because we're dealing with an annual interest rate, and the formula PE to the RT is written in terms of time in years. So that 8.66 is time in years, and maybe you don't have a lot of intuition about this, but that is a reasonable amount of time for an investment to take to double. So there you go. That's the solution to this account doubling problem. Now, you may have noticed that right here at this step, we divided both sides by that 5,000, and the 5,000 and the 10,000 simplified down because we divided and we just got 2. It turns out that you don't actually need to know what the principle is to solve a doubling time problem. I'll say more about this in a future lecture, but it's because right here at this step, whatever you put here is multiplied by 2 over there. So when you do this first division step, the principle actually cancels out completely and you're just left with 2. So just something to keep in mind, and I will say more about that in a future lecture.